This lecture will be on evaluating a function and reading a graph. So we already know a little bit about this. Let's start with an example. If we're given the function f of x equal to 2 times absolute value of x minus 1, we know that this is the function notation that tells us the function is called f, x are our inputs, and the rule that the function is following is 2 times the absolute value of x minus 1. So if we want to calculate the following values, like f of 0, that just means replace x by 0 on the right side. So that's f of 0 is 2 times absolute value of 0 minus 1, which is 2 times absolute value of minus 1. Absolute value just gives us back the positive part of the number, so this is 2 times 1, which is 2. So I would say f of 0 is 2. F of 2 means replace x by 2 in the function, so that would be 2 times absolute value of 2 minus 1, which is 2 times absolute value of 1, which is 2 times 1, and that's also 2. If I put in f of negative 2, then I'll replace x by negative 2 in the function, so it's 2 times absolute value of negative 2 minus 1, which is 2 times absolute value of negative 3, which is 2 times 3, which is 6. But I can also input expressions. So if I see something like f of x plus 1, the process is still exactly the same. I just replace x in my function by whatever is here inside the parentheses. In this case, it's x plus 1. So that's going to look like 2 times absolute value of x plus 1 minus 1, which is 2 times absolute value of x. So that will be my answer here. F of x plus 1 is 2 times absolute value of x. If I replace x by x squared plus 2, that's f of x squared plus 2 is 2 times absolute value of x squared plus 2 minus 1. That's 2 times absolute value of x squared plus 1. So that will be my answer. When I get to the point where there's nothing else I could simplify, then I just stop. If I wanted to, I could multiply by 2, but I'm not really sure, so I'm just going to stop, and that's perfectly fine. So what if I have 2 over t inside parentheses, and my function is x over x minus 1? So the process is going to be exactly the same. I'm going to replace anywhere I had an x, I'm going to replace it by 2 over t. So on top, this is 2 over t. So this is f of 2 over t is equal to 2 over t divided by 2 over t minus 1. So I need to try and simplify this. On top, I can't really do anything yet. It's just 2 over t. On bottom, I should be able to get a common denominator by multiplying this minus 1 by t over t. Then I'll have 2 over t minus t over t on bottom. That's going to be equal to 2 over t over. I can combine these as one fraction and make this 2 minus t over t. Now, I have 2 over t, and all of that is divided by 2 minus t over t. So the rule of division, when I have a fraction divided by a fraction, is that I keep the fraction on top. I change division to multiplication, and I flip or invert the other fraction. So this becomes t over 2 minus t. Another way of thinking about this, the way that I always like to think about this, is that if I wanted to cancel this denominator on the bottom, then I would need to multiply by t over 2 minus t. And whatever I do on the bottom of the fraction, I need to do the same thing on the top to make it just multiplying by 1. So I can think of it as multiplying by t over 2 minus t on the bottom, and this will cancel and become 1. And I can think about it as multiplying by t over 2 minus t on the top. Well, that's exactly what I've written here off to the side. Okay, so then to multiply fractions, I just multiply straight across the top and straight across the bottom. So 2t on top and on bottom, t times 2 minus t. And then these t's, it turns out that they cancel. So this becomes 2 over 2 minus t. So 2 over 2 minus t is going to be the answer for this evaluating f at 2 over t. So I'm going to do something very similar here, evaluate f at 2 over t plus 2. So I go back to my original function, f of x is equal to x over x minus 1, and everywhere that I have an x, I just put 2 over t plus 2. So f of 2 over t plus 2 is equal to 2 over t plus 2 divided by 2 over t plus 2 minus 1. In this way, I've just replaced every x by 2 over t plus 2. And I'm going to repeat the exact same process. I want to get a common denominator on the bottom, so I write 2 over t plus 2 on top, nothing changes. On the bottom, I have 2 over t plus 2 minus t plus 2 over t plus 2. So then, if I want to write the bottom as one fraction, that's going to become 2 minus t minus 2, because this minus gets distributed to the t and to the 2, and all of that is over t plus 2. So I know that this is going to become 2 over t plus 2 times t plus 2 over, then 2 minus t minus 2 is just minus t. So this is 2 over minus t, or minus 2 over t. So that is my answer. I just make sure that I'm very careful as I'm working through these steps and taking care of things like distributing minuses and finding common denominators and properly combining fractions. So the best way to go about it is just step by step, slow and steady. All right. Now, solve f of x is equal to 3. So we have f of x is equal to x over x minus 1, and we want to solve f of x equals 3. So that would be solve x over x minus 1 is equal to 3. And we want to solve for x. Which value of x gives us x over x minus 1 equals 3? So I know that I want to clear denominators, and I know that I can do this as long as we're not dividing by 0 on the bottom. So I want to be really careful if x was equal to 1. Let's put it in red. If x equals 1, in this case, I've got a problem because the bottom of my fraction is x minus 1. So just for a minute, let's assume x is not 1. And let's multiply by x minus 1 on both sides. So on the left side, clearly that cancels out and that just leaves me x. And on the right side, I have 3 times x minus 1. So I have x is equal to 3x minus 3. And I know this is a linear equation. I want to move all of the x terms to one side, all of the constant terms to the other side. So let's subtract x from both sides. I get 0 is equal to 2x minus 3, and add 3 to both sides, so I get 3 is equal to 2x. Then divide both sides by 2, so x is 3 over 2. So that I didn't get x equals 1, so that's a good thing. And I just need to now check my solution into the original equation. So I'm thinking x equals 3 over 2 is my potential solution. Let me plug that in to the original equation f of x. So 3 over 2 divided by 3 over 2 minus 1. Well, that's 3 over 2 divided by 3 over 2 minus 2 over 2, which is 3 over 2 divided by 1 over 2, which is 3 over 2 times 2 over 1, which is 3. That's exactly what we wanted. So we're going to say that x equals 3 over 2 is the solution to the equation. All right. In the next example, we're taking f of x equal to x plus 5 divided by x plus 2. And it asks us, then the domain of f is the set of all real numbers except, and we kind of have to fill in this blank here. So we know our rule of thumb for finding domain is we want to make sure that we don't divide by 0, and we want to make sure that if we are having even indexed roots, then we're taking an even indexed root of something greater than or equal to 0. Well, I don't see any even indexed roots here, so the only issue I might run into is if the bottom of this fraction were 0. So if x plus 2 equals 0, then that would be a bad point. And that would mean if x was equal to negative 2, then that would be a bad point. So to fill in the blank, the domain of f is all real numbers except negative 2. And how do we write that in interval notation? That's going to be negative infinity to negative 2. We talked about this in the last video, union negative 2 to infinity. So we're literally taking everything less than negative 2. We're going all the way up to negative 2, but we're stopping and we're taking out negative 2, and then we keep going to infinity. Okay, then it asks us to evaluate f of 2. So f of 2 should just be equal to replacing x by 2 in the equation. So 2 plus 5 over 2 plus 2 is 7 over 4. That should be f of 2. If we have f of t plus 1, then everywhere that I have x in the equation, I replace x by t plus 1. So this becomes t plus 1 plus 5 over t plus 1 plus 2. That's t plus 6 over t plus 3. And I can't really simplify it anymore, so I would just leave it here. And that should be t plus 6 over t plus 3. Now what about f of t squared? So when I have something like this, where maybe I need to apply more than one function, then I'm going to work from the outside, from the inside out. So let me first deal with this much, and if I can figure out what this much is, then I will know what to plug in to my function f. So let's start with f of t squared. Well, f of t squared just means replacing x by t squared in the function, so that's t squared plus 5 over t squared plus 2. And I can't really do anything to simplify that, So I'm going to stop there, and now I see that I want to plug all of that into f again. So remembering that f of x is x plus 5 over x plus 2, I'm just going to replace each x by t squared plus 5 over t squared plus 2. So then f of t squared is f of t squared plus 5 over t squared plus 2. So that's going to be equal to t squared plus 5 over t squared plus 2 plus 5 on top. And on bottom, t squared plus 5 over t squared plus 2 plus 2. So I just replaced each x by f of t squared. And now I'm going to find common denominator. So I'm going to say, well, on top I need t squared plus 5 over t squared plus 2. I want this 5 to also be over t squared plus 2. So I'm going to multiply by t squared plus 2 over t squared plus 2. And I'm going to go ahead and distribute this 5 on top. 5 gets multiplied by, that should be t squared plus 5. Let me fix that. T squared plus 5. Oh no, I'm sorry, t squared plus 2 over t squared plus 2. Because I'm just multiplying by 1 to get it over a common denominator. All right, so here that gives me plus 5t squared plus 10 over t squared plus 2. That's just the top of the fraction. I'm going to do the exact same thing on the bottom. I'm going to multiply by t squared plus 2 over t squared plus 2 to get a common denominator. So then I can say this is t squared plus 5 over t squared plus 2 plus, and distribute this 2 across, that's going to be 2t squared plus 4 over t squared plus 2. So I'm getting a little closer, but I've still got some work to do. I'm going to write the top as one fraction. I'm going to say this is t squared plus 5 plus 5t squared plus 10 over t squared plus 2. And then the bottom is t squared plus 5 plus 2t squared plus 4 over t squared plus 2. Let's see if we can simplify this a little bit by combining like terms. I can, on the top of the top, I can combine t squared and 5t squared, so that's 6t squared. And I can add 5 and 10. So this becomes 6t squared plus 10 over t squared plus 2. Then here I have t squared and 2t squared, so that's 3t squared plus 5 plus 4, so plus 9, over t squared plus 2. And the last thing that I'm going to do is flip and multiply. So I have 6t squared plus 10 over t squared plus 2. And then, because I'm dividing by a fraction, that's the same thing as multiplying by t squared plus 2 over 3t squared plus 9. And then I have t squared plus 2's will cancel. So this ends up just being 6t squared plus 10 over 3t squared plus 9. So again, just taking it step by step, I was able to simplify everything. 6t squared plus 10 over 3t squared plus 9. Okay, now let's talk a little bit about reading graphs. And we already know a little bit about reading graphs. But in particular, we want to learn about increasing, decreasing, and constant behaviors of graph. So this blurb here tells us that a function is increasing on an interval. We know what an interval is, and we know an open interval means that we're not including the left endpoint and we're not including the right endpoint, but we're including everything in between. So it's increasing on an interval if whenever we take x1 and x2 in the interval, and we take them specifically so that x1 is the smaller one and x2 is the bigger one, then that should mean that the function evaluated at x1 is also smaller than the function evaluated at x2. So we can look at this first picture here to sort of understand what it's saying. It's saying, let's say we have an interval. This is the interval. And over that entire interval, no matter which 2 points I choose, so let's just say I've randomly chosen these 2 points, but I could have chosen any 2 points. I could take this one and this one, for example. Then if I have the smaller point, then its function value should be smaller than the larger x value. Its function value should be larger. So that's all it means to be increasing. That if we can find an interval, open interval, over which no matter which pair we choose 2 x values, the smaller x value corresponds to the smaller y value, and the larger x value corresponds to the larger y value, then we say this function is increasing over this interval. Okay, a similar notion is decreasing. So again, we start with an open interval. We just pick 2 points in the interval. If the function is decreasing over the interval, then it means that the larger x value now corresponds to the smaller y value, and the smaller x value now corresponds to the larger y value. So if it helps to draw a picture like this, it's absolutely a good idea. So as we're moving from left to right, the increasing function, the values are increasing as we move from left to right. For the decreasing function, the function values are decreasing as we move from left to right. Constant just means that the y values don't change as we move from left to right. So you still take an open interval, you still pick 2 points, then the smaller of the x values is going to correspond to exactly the same y value as the larger one. Then we call it constant, no change. Okay. So let's look at an example where we're asked to look at a graph and determine the intervals on which the function is increasing, decreasing, and constant. So remember, we're thinking about moving from left to right across our graph. So as I'm moving from left to right, say from here to here, are my y values getting bigger or are they getting smaller? Well, from here to here, it looks like they are getting smaller as I move from left to right. Whereas from here to here, when I'm moving from left to right, my y values are actually getting bigger. So the y values getting smaller as I move from left to right is going to be called decreasing. So I'm going to say decreasing. And I know that these arrows mean I'm going off to the left forever, so that's from negative infinity. And when do I stop decreasing? Well, right around x is equal to -1. And remember, we always do this for an open interval. Why open? Well, because at this point where it changes from decreasing to increasing in this example, so here's, get my pen, here's the x value, x equals -1. At exactly this point, It's impossible to say whether the function is increasing or decreasing. It's in between. At a single point, the function is neither increasing nor decreasing. So we don't include -1 in either of the intervals. So it's decreasing from -infinity, oops, that should be negative, to -1. And then what about increasing? Well, picking back up on the other side of -1, so that means the open interval that does not include -1, but includes everything bigger than -1 all the way up to infinity. Again, you can see that -1 is not included in either of these intervals because at -1 we can't say that the function is either increasing or decreasing. Okay, and we didn't have any intervals where the function was constant in this case, but that could be a situation that you would run into, and then you would just write down the intervals over which it's constant. Okay, so this kind of brings us to the concept of relative maxima and minima. The points at which a function changes its increasing or decreasing behavior can be used to find the relative maxima or relative minima of the function. So looking back at our previous example, exactly what we talked about, when the x value is exactly -1, is right in between where the function is decreasing and increasing. So we can think of it as the point that it changes from decreasing to increasing. And then if you look at the graph, it turns out that when x is equal to -1, that's exactly a minimum for this graph. So this concept of relative maximum and minimum is closely connected to this concept of increasing and decreasing. And what do we mean when we say relative? Well, we mean relative to the values around it. So looking at this picture here on the right, this point is not necessarily the absolute minimum because this graph goes down, 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 down. So we've got y values that are smaller. So what we mean by relative minimum is that it's smaller than all of the values nearby. Or relative maximum, in this case, means it's larger than all of the values nearby. Because again, this side of the graph goes off and we do have bigger y values. So that's what the word relative means. It just means relative to its neighbors. Okay, so to formalize that, a function value f of a is a relative maximum of f if there exists an open interval containing a such that f of a is larger than f of x for all x in the interval. That's exactly the picture that I drew. I drew a little open interval around it. If we can find any interval, any little open interval, where a is the smallest value, then it's a relative minimum. Or if we can find any open interval where a is the largest value, then it's a relative maximum. And that's what these two things say here. So if we look at a graph, we should now be able to determine the numbers at which the function has a relative maximum, a relative minimum, and what the relative maximum and minimum values are. So given this graph, we're asked to first find the number at which the function has a relative maximum. So relative maximum means that I can find an open interval around which all of the other points are smaller. That looks like that should be this point here. Because if I took a little interval here to the left and right, then all of the values inside this interval are smaller than the function value here. So the answer to part A, the relative maximum occurs at x equals -1. So we say that it occurs at the given x value, but it also asks what is the maximum value? So that means what is the y value at this x equals -1. So the relative maximum value is y equals 4. So another way of thinking about this is that we have the ordered pair -1 and +4. So the x-coordinate gives us the location that the maximum occurs, and the y-coordinate gives us the value of the maximum itself. Okay, what about relative minimums? So question B, the numbers at which the function has a relative minimum. So again, looking at this picture, it seems like it should be here and here, and these ordered pairs are -2 and 0, 0 and 0, because if I take a little open interval around each of these points, then I have all of the values in the open intervals around them are bigger than them. So these are going to be our relative minimums, and the numbers at which they occur are the x-coordinates. So we'll say the relative minimums or relative minima occur at x equals -2 and x equals 0. And the relative minimum values in this case, they're both 0, but theoretically they could be different. Like if this picture looked like this and then this, these would still be relative minimums, and they would have different relative minimum values. Okay. So this question, we have a graph, and we're asked to use the graph to determine the domain, the range, the number at which the minimum occurs, the value of the minimum, the zeros, the f of 0, f evaluated is 0, the values for which f of x is -2, etc., etc. So let's go one by one. And this is going to be kind of one example to combine a lot of what we've learned so far. Okay, so first of all, use the graph to determine the domain. So we know that the domain is the collection of all of the x values in the relation or the function. And in this case, we have a function because it passes the vertical line test. So because of these arrows that tell me that this graph goes forever to the left and forever to the right, and I don't see any breaking points in the graph, the domain is just all real numbers. The range we know is the collection of all of the y values. So I can see here that below this line, y is equal to -4, the graph doesn't have any values. But above the line, y equals -4, it takes all of the values, and again, that's because this arrow keeps going off to infinity. So we get to say that it's a -4, and I'm including -4 because it does have the value -4 here. -4, everything to infinity. So that takes care of domain and range. Then it asks the number at which f of x has a relative minimum. So f has a relative minimum at x equals, well, this point is in fact the relative minimum, because if I take, say, this open interval around it, all of the values inside of the open interval are larger than its value. So this occurs when x is equal to 4. So that's the number. And then what is the relative minimum? The relative minimum value is y equals -4. And in this case, this is also the absolute minimum, as we talked about, because the range doesn't include any smaller values, but we know that a relative minimum doesn't have to be an absolute minimum. Okay, the zeros. By the zeros, it means the x values at which the function takes the value 0. Another way of saying that is the x-intercepts. So instead of zeros, let's say x-intercepts. But zeros is another way of saying the same thing. So the x-intercepts. And when we're talking about intercepts, we remember we're always talking about ordered pairs. So we have the ordered pair 1, 0, and the y-coordinate of the x-intercept is always 0. So the x-intercepts are 1, 0, and 7, 0. How about f of 0? F of 0, well, that's just another way of saying the y-intercept. And the y-intercept is also an ordered pair. And we know its x-coordinate is 0. So when the x-coordinate is 0, what is the y-coordinate? 4. So the y-intercept is 0, 4. Now, they asked which values of x, for which values of x do we have f of x equal to -2? F of x is equal to -2 when x equals. So how am I going to answer this? I'm going to look at the y value -2, and I'm going to see which x values correspond to that y value. And there are x values that correspond, so f of x is equal to -2 when x is equal to 2, and when x is equal to 6. Okay. It also asks us, is f of -1 positive or negative? So we go to x equals -1, and we find the corresponding y value by just looking up or down. We see that it's here. So f of -1 is positive, since f of -1, in this case, we see that that's actually equal to 4. Okay. We're going to find where is the function increasing, decreasing, and constant. So let's say increasing. So what am I looking for when I'm talking about increasing? I'm talking about as I'm moving from left to right, I'm seeing, are my function values getting bigger? So if I start on the furthest side and I go like so, the function values are not getting bigger, and they're still not getting bigger, and they're still not getting bigger. So it's when we get here to the relative minimum, then we find that the function values to the right are getting bigger. So they're increasing, and that starts happening here when x is equal to 4. So we say from 4, and this graph goes all the way to infinity on the right. So from 4 to infinity, and remember when we're talking about increasing or decreasing or constant, it's always an open interval. So what about decreasing? Well, I do the same thing. I move from left to right, and I see over which interval are the function values decreasing, and it looks like it's here between the y-axis and x equals 4. So that would be from x equals 0 to x equals 4. The function is decreasing. And then finally, where is the function constant? If I move from y to left, if I move from right to left, from left to right? Is there a part of the graph where the function values are staying the same? Yes, absolutely there is. It's this left side of the graph, and again we have an arrow here, so it continues doing that forever and ever. That means from negative infinity until we got to x equals 0, it was constant. So I just want to point out here, as I said, these intervals are always going to be open because we don't know at the point where it's changing behavior. We can't say which interval it should be included in. So these are always open. And we're talking about subsets of the domain. So we don't want to get confused with the range. When we're talking about increasing, decreasing, or constant, we're talking about which x values. So these are sets of x values. And one other thing to notice is that the function cannot be simultaneously increasing and decreasing. So these should be different intervals. And if we look at what we found, they are, right? We split the domain up into the piece from negative infinity to 0, we're constant. Then the piece from 0 to 4, we're decreasing. And then the piece from 4 to infinity, we're increasing. So these should all be different sets of x values because the function can only be one of the three things, increasing or decreasing or constant at any given point. Okay, we're almost done. The question also asks us to find where the function is greater than 0. So we took care of increasing, decreasing, constant. Where is it greater than 0 and where is it less than negative 2? So the function is greater than 0 so now I look at my y values. The value y is equal to 0 corresponds to the x-axis. So everything here above the x-axis, my function is greater than 0. Let me actually use a different color. So here, above the x-axis is where the function is greater than 0. Okay, so if we want to express that in terms of interval notation, we would say, well, it's definitely everything from negative infinity all the way until x equals 1. And then I'm not sure whether or not to include x equals 1. The question said greater than 0. At x equals 1, it's equal to 0, so we're not going to include. But there's more. It's also greater than 0 here on this other side. So from x equals 7 going off to the right, so remember we have this union symbol to say 7 and going all the way to infinity. So we say when x is in this set, negative infinity to 1, as well as 7 to infinity. And then lastly, where is the function less than negative 2? So I've already got the line negative 2 kind of dotted out here. That's here. So where is it less than negative 2? It's going to be this part of the graph. And we want to know what part of the domain corresponds to that part of the graph. So it should be from x equals 2 to x equals 6. So I'll say the function is less than negative 2 when x is in the interval 2 to 6. And we don't include 2 and we don't include 6 because it said less than, not less than or equal to. All right. So we have one more topic that we want to introduce before we call it a day, and that is the difference quotient. So the difference quotient is closely related. If you keep studying math and you take pre-calculus and then maybe you take calculus, you'll see this come up again and again, but even for us here in college algebra, this is going to be an important concept. Whenever we see f of x plus h minus f of x all over h, this is called the difference quotient for a function f. And let's think about, say, some function. Maybe it looks like this. And let's choose some point on the axis. This is the x-axis, and say this is our x value. And then h is some positive number or some non-zero number. Let's say this distance is h distance. Then this x value is going to be x plus h. So what do we mean when we say f of x plus h minus f of x all over h? Well, let's think about it here. F of x plus h is this point, and f of x is this point. So probably I should draw my function just a little bit differently here. So that these don't have the exact same function value. Okay, so here we go. Here's my f of x plus h. It's a little bit lower. So what do I mean when I say f of x plus h minus f of x and then over x? Well, I'm just finding the slope of this line. So the difference quotient gives us the slope of the line, the straight line, connecting any 2 points. So we may know how to find the slope of a straight line. What the difference quotient is going to allow us to do is, even if we have a curve, the idea is, well, let's just draw the line that connects the points of the curve. And then by taking the difference quotient, we can kind of guess about the slope of the curve. And that's probably about as much as you need to know for now. So we want to know this difference quotient, and we want to know how to apply it to a function. So if we're given a function like we have here, f of x equal to 2x squared plus x minus 1, we know, because we know how to use function notation and we know how to evaluate, that when we see f of x plus h, that just means replace x by x plus h in the function. So let's just do this piece by piece. Let's start by looking at what is f of x plus h. This is 2 times x plus h squared plus x plus h minus 1. And it asks us to simplify. So let's go ahead and multiply this x plus h times x plus h. So that's going to be 2 times x times x is x squared. Then we have h times x. And then we have h times x, and h times h. So this ends up being 2x squared. Now, hx plus hx is already 2hx. Then I'm multiplying it by 2, so that's 4hx plus 2h squared plus x plus h minus 1. So this is f of x plus h. What else do I need for my difference quotient? Well, I need minus f of x, and then I want to divide the whole thing by h. So if I put it all together, I have f of x plus h minus f of x all over h. Well, that's going to be equal to this thing, 2x squared plus 4hx plus 2h squared plus x plus h minus 1 minus, I'm going to subtract all of f of x, so minus 2x squared plus x minus 1. I'm putting it in parentheses so that I remember to distribute the minus. And then it's all going to be divided by h. So that's 2x squared plus 4hx plus 2h squared plus x plus h minus 1 minus 2x squared. Now I'm distributing the minus, so minus x plus 1 all over h. Let's see what we can cancel. I have plus 2x squared and minus 2x squared. I have plus x and minus x. I have plus 1 and I have minus 1. So this looks pretty nice. So this is just 4hx plus 2h squared plus h, that's all I had left, and over h. So it seems like I can factor h out of all of these. I can say this is h times 4x plus 2h plus 1 over h. I just factored h out everywhere. And then I can cancel the h's. So finally I have 4x plus 2h plus 1. So the difference quotient for this function is 4x plus h plus 1. And that will be my final answer. So I'll box it off. Okay. So you can see that we still have h in this expression. So going back to the picture that we drew, that tells us that depending on which h we chose, like I could have taken this point and this point, the slope of this line is different than this one, right? So that's how we interpret that. Depending on which h we choose, the slope of the line changes. And that is the final skill that we wanted to pick up for this lecture note. So we'll go ahead and stop recording now and pick it up in the next lecture.